Today we will try to do a toy problem profiling with PyTorch Profiler. So PyTorch is one of the more popular machine learning frameworks that we can use to build machine learning models or deploy existing models that comes out of big players, for example. And one way to know what these big models that we download from here and there are doing out of the box without messing around the code at all is using the PyTorch profiler. And traditionally, profiling tools have been used to identify performance bottlenecks and critical points which we might have to pay special attention to, try to modify, change, and make our code better. But in this age where we have serious dependency on code written by somebody else, profilers could very easily be used as a nice learning tool. So what does profilers do? Profilers usually tell us lots of things, but what I found more useful is operator execution time. It will give us the CPU operations and how long it took for an operation to happen, and GPU kernel calls time, and also the execution details. More useful for us is operator input shapes. For example, when we try to train a model, we always think about what are my token sizes, what should be my sequence length, and how these things are being deployed actually inside the code. We can understand that by looking at the operator shapes. What type of arrays are going in, what size is coming out, that we can find out through a profiler. And then it gives us stack traces. For example, Python call stack, which script, which line number is eventually deploying this kernel. When we try to actually get the maximum out of the hardware available to us, these details become important. And Profiler can do that for us. Another thing is looking at how good a random model is using my hardware. Should I buy a new GPU, or my current GPU is still okay? We understand that by looking at the flops, floating point operation, and profilers these days, PyTorch profiler especially, would count the flops for us for all the matrix multiplication type operations that are happening. And to be fair, a large chunk of transformer architecture is basically doing matrix multiplication at somewhat lower precision with various shapes and sizes. And finally, the most useful thing is the execution timeline. What happened first? What next? Are there empty spaces? Can we make this launch and execution faster, etc., etc.? So these are the useful things that we get from a profiler, and this profiler comes with the framework that is most popular. So one less thing to worry about being installed in our system. Okay, did that make sense? Questions? Nice. So now that we have our, yes.
Yeah, the flops, you said it is counted by PyTorch?
Yes.
Or is estimated?
No, so the PyTorch profiler will print out the number of flops for a specific kernel.
I mean,
if you are using a gem kernel of some shape under the hood, PyTorch profiler will print out the flops that it has calculated throughout the time you have profiled for.
So this is counted by the PyTorch, right?
Yes, sir.
Okay. Are you sure?
That's a very good question. I have to open the box even further, but they are fairly close to the numbers I would calculate by hand.
Okay. So for the jam corner, right? So it's kind of
Yes.
simple. I mean,
Yes.
easy to expect. So,
Yeah.
okay.
But it's a first shot at this. So for example, this will be the first thing that we look at. And if we need some more details, we have other methods. So now I have tried to make a simple example and give you the Git repository. And here are the simple instructions that we can follow and try to run this on Aurora. The first thing that I would do is I would clone the repository, cd into the top level directory, and then switch to the data science 2025 branch. So how many of you are planning to follow along? Okay, lots of people, good. So once you have the clone and switch done, request for a interactive session, and we will go from there.
Khalid, do you want to show it in the terminal yourself too?
Oh yeah, that's a very good idea. Nobody can read this. Is this better?
Yeah.
A little bit more, maybe? Cool.
For a space in the front, if you guys want to make sure that.
Okay, so inside the top level directory, we have a data science directory. And inside the data science directory, we have AI/ML profiling directory. And should resize. Okay, and then I will go to my I will request for 2 nodes and see how long it takes to get those. So inside the profiling directory, I have put 4 Python files, an environment file, and 4 run script. We will be trying to run these 4 scripts. 2 of them does not generate profiles, and 2 of them does generate profile. And we'll try to run them and save the traces ourselves and see how it goes. So now I will switch to the markdown file and talk a little bit about what we are trying to do in these Python files. Okay. So the first of the files there is a file that ends with the extension .env. So this one is our Panda environment. So to get the installation of PyTorch 2.8, we have to load different modules, and sourcing that file would do that for you. If you are in your login node, you can try to source that file, and I have not found the node yet. Source that file and check the Python version. Once you have sourced the file, export this environment variable ze flat device hierarchy flat. Just copy and paste should work nicely. So what this environment variable does is it gives the 12 tiles in the compute node as independent devices, so that we can use these 12 tiles as 12 GPUs. Okay? And then you can just do import torch and check torch version. Questions, difficulties? Waiting for the node to come? That's okay. So has anyone got a node? You have gotten a node? And could you source the environment? Oh, okay. You do not find. Let me quickly.
Waiting for their session to start.
Yes. So yes, Git
The
Tweet
LTF
Data Science
training,
2025.
You've submitted with the LCF training project and you're using the reservation ID on the appropriate machine. It starts with an R, I think, or no, it uses the HPC. Oh, okay.
You did
So
the
it's like a
Git-
routing queue or whatnot.
Would you please
Okay.
go to the?
There should not be any waiting. There's 128 nodes in that reservation, so I'm trying to follow up with our
and where did you
local
start the client
expert
from?
to see what's going on and why are you guys sitting and waiting?
I guess maybe I had an old one. Maybe.
Yes, I think so. Like, let's start fresh and see. Okay. Okay, we have a better way of doing this.
Okay.
May I?
Yeah.
There we go.
Get out of the way.
No, that's fine. It's not an empty repository. Go away. Nice.
But I just need to do like a git pull.
Oh, you are doing it inside the, you are doing it inside the compute node.
Yeah.
Maybe we should do it in the login node. The cloning, we should do it in the login node. Okay, it is not. Do we have a session here? Okay, so how do you get in? Please get inside Aurora. How about others? Found something?
I can do it in Polaris. Is it fine? Or?
No, I mean, this thing I have written and it has to be Aurora. No node yet? Cool, nice. So I can do it here?
Mhm.
Okay, so do we have the guy? Oh, sorry, Git clone. GitHub permission denied public key. So you have to set up your key so that you can clone the repository nicely. Okay, so you have to go to your profile and you have to set a key.
So as a node, we don't have the large reservation anymore. due to lack of usage. So we only have the ALCF training queue, but we remove the limit. So you should be able to submit
Say.
from 1 to 128 nodes.
Integration key.
Depends on the size of your job.
Okay, so now
But its
it-
queue and the project are all basically the same name.
have been able to clone the repo? Okay, good. Switch and you could find the things that I'm showing? Nice. Okay, good. Now, let's try to, they're happy that you have added this one. Okay, let's see. This repository is a little bit fat. We should trim and see how it goes. CDL, CF, hands-on HPC workshop. Oh, disable that key. Git branch -v. It could be there is a problem with my repo. Data science 20. You made a last check run. That's me. Yes. Okay. Git which data science 2025. Okay. Science filing. AI profiling. Oopsie. CD. Now we go back to your compute node. So what we do is pwd, copy this and paste this. So life is now trial by fire. I'll try to source this guy. There we go. And Python. Okay. Import torch. It sometimes takes a little time for the import to happen. Let's see. I expect it to work. If it works, I'll be very happy, but let's see how it goes. Nodes, yes, sir.
Okay, it just became ready just now.
Nice. Okay.
Come to do this.
CD into that directory, like ALCF and so on, data science, AIML profiling directory. Let's CD into that.
Right now, which
And so you're in the home. Okay, so where is your cloned repository? Oh, it's in your home. Then it's easy. CDL. Wow. Tab completion works. Data science, AIML profiling, LS. Oops. And we have this guy. So what we are trying to do is source. It has activated these two Conda environments. And then we can just do Python. It will give us an interpreter. And then we can try to do import torch. It takes a while for these many different files to come from the file system, which is like a server based, and then it comes and sits inside our memory, and that takes a little while. I expect it to work. Let's see how it goes. Did it work for you, ma'am? Yes, no errors. And then we do torch dot dunder. Oopsie. There we go. Nice. It's waiting for a node. Yeah, see, they canceled our reservation.
No, we just removed the large reservation. We still have the small, which is 128 nodes.
Should be fine.
So,
We're
but there's
just-
an issue with the queue right now. So
Okay.
we're trying to resolve it.
Cool.
Yeah, I am also submitting to the queue and I'm like on the waiting to get a node. So there should,
That's okay.
yeah. We're aware of it. We're trying to fix it.
That's okay. Okay, so now, oh, your import torch is still happening. Wait for it. It worked for one. So I expect it to work for you too. Yeah, it takes a while because it's coming from a file system. So what I tried to do is I tried to make it world readable. So when you are trying to do it, you do not run into any permission issues, which are like, I mean, not funny. I hate them the most. So that's why I tried to put it somewhere where we will have list permission issue. But in the process of trying to achieve that, I had to put it in a remote corner so that it takes a while for all these files to be copied over to the memory of our node. And that's why it takes time.
When I log in, I get a message about permissions.
Yes,
Is that normal?
usually it's normal. Like you could log in only because your permissions are up to a certain degree.
That's the permission I don't have.
Exactly. So, but yeah, let's say I'll walk around a little bit and see how is it going. No problem. But the clone went okay. We could switch and find. Nice. You got the node. Nice. Good one. CD into that directory.
Yeah, so I'll try this.
Yes, yeah. CD into that directory. Like it's 2 level deeper inside the
Data science.
top level directory, then data science and AI/ML profiling, and try to activate the Conda environment. Hello, sir.
Get that code and let's.
Oh, that's okay. So are you inside Aurora? Oh. Sorry about that. Got a compute now? For a few interactive session. I like, I mean, accidentally probably hit Control C, but that's not. But you have been able to clone the repo and things look normal, and you can see these files. I switched to the branch, and you can see this markdown file there, and the env file, yes, please do. Few minutes, I give up. And submit another one. Yes. Yes, I made some. I can do it.
10:30.
10:30? Okay, great.
Okay. Somehow, one of the jobs allocated all the GPUs. I know this is still a bug on our side, so it's not the user's fault. But yeah, okay. You locate the user more anonymously than via the microphone. But I don't have any idea how this could have happened. Yeah, just exit out of the interactive shell and resubmit. So weird.
Okay, so it seems most of my users are in business, right? We have a Git repo that we have been able to clone. We have the codes handy, and we have a compute node where we can run things. So now let me check the status of mine. Okay, I'm here. So the first thing that we are going to do oh, look at that. This is nasty. Okay. So now the first thing that we are going to do is source the environment file. And this will give us a Conda environment. And inside the Conda environment, we can try to import Torch. This takes a little bit of time, and then look at the Torch versions. And we can also run a few commands which tells us a little bit more details about the hardware that we have. How many GPUs we can see, and each GPU have however much memory, has FP64 support, and standard stuff. But that gives us an idea about what is the system that we are dealing with. So I believe most of you are past that point. And once we have learned a little bit more, we will try to understand what is needed to run a piece of code that works, for example, on an NVIDIA GPU, and bring it and run it on an Intel GPU. So the AI frameworks are in general fairly portable. By fairly portable, I mean the changes that we have to by hand make to the code are fairly straightforward. For example, the first thing that we would like to do to run on an Intel GPU is import Intel extension for PyTorch. So the idea is this extension library gives us kernels that are called by PyTorch, but these are written specifically to leverage the Intel GPU in a more performant fashion. So we need that line. And then if you have some experience with PyTorch and CUDA, I would expect you to be familiar with torch.cuda.something type API calls. For example, here I'm showing torch.cuda.device count. So this, in principle, should tell us how many GPUs it can see. And torch.cuda should be replaced by torch.xpu. So xpu is naming trying to differentiate from a GPU, for example. And also some other type of devices could be wrapped inside X. It could be a different kind of accelerator. It could be an FPGA, etc., etc. Because this backend has been written in SYCL, which in principle can run on multiple accelerator. But today we will limit ourselves to the Intel GPU. Now, the third that we have to do is, again, we write something, and if we do not instruct explicitly, it will be in some memory. We want to send that thing inside the GPU memory. So that would be PyTorch's .to API. So in a CUDA code, we will have our model 2 with a string CUDA. For an Intel GPU, the model should go to XPU, right? So these are the three basic things that we must do if we try to port a piece of PyTorch CUDA code to PyTorch XPU code. But today you are not going to do that. I have done all that and put a Python script there. I'm just saying it so that you have an idea what you may have to do. And then comes the standard machine learning training block. We have figured out our device, which is an XPU device. We have sent the model to the device, and we have fixed our training criteria, loss, etc., etc., sent that to the device, and finally, we call the model an optimizer with Intel extension for PyTorch wrapper, so that the model, when trying to calculate loss, uses the performant kernels provided by the Intel extension library for PyTorch. Make sense? Questions? Good. So now, oh, okay, my import torch happened. Torch dot under version. It's a 2.8, which looks nice. And let's try to do some more interesting things. So first, let's try to run a simple transformer model, which is the vanilla PyTorch transformer model. This comes by default with PyTorch, and then we will try to run a full training loop with some synthetic data on however many GPUs we want. Because we have one node at this point in time, I have written the code to take advantage of the 12 tiles on a node. The code is written as such, it will run at any scale. So let's look at the job script first. That will be run DDP PyTorch 2.8 and 1 or 12. So the job script is very simple. It sources the environment, sets the device hierarchy to flat so that we have 12 GPUs instead of 6. We could do it the other way as well. In that case, we will have fat GPUs. Here we have more GPUs. And then some process launcher. Line 10 is very important. So line 10 is trying to enable resources based on the Aurora node architecture. We will come to it a little bit later. line 12 has this ZE affinity mask. This ZE affinity mask is equivalent to your CUDA visible devices. I'm telling it that you should expect 12 tiles, 12 GPUs. Go look for them and let me know if you cannot find them. That's what this environment variable do. And after that, we have this simple MPI exec. MPI exec run on 12 nodes, 12 ranks, and we will be running 12 processes per node. These doesn't matter. CPU bind, we will talk more, and then Python, PyTorch 2.8 ddp.py. Makes sense? A Python call wrapped by MPI so that it goes there, run the same copy of this Python code on 12 GPUs. Questions? Okay, cool. Now, fire it off. Hopefully it will run. I actually cannot see what's happening. Bash. Why can I not see? Around DDP PyTorch. Oopsie. I have to do a resize. Okay. Nice. Okay. And bash run DDP PyTorch 2.8 and 1. Oopsie. There we go. Let's see, if it starts running, I will go back to my markdown and talk about the main part of the code where we set up a transformer, set up some inputs, which are random numbers, and set up the training loop. Okay, so this bit is the main part of the code that we are running today. And the important bits are the Intel extension. We tell it that we have an XPU device, and then we set some random numbers as our data sets. You can think of the source as your input prompt. And then the target is basically what the transformer spits back at you. And then we make a data set using torch.utils.data, and then we initialize a data loader which will read things in the batch size of 32 tensors at a time. And then we have the model, torch nn.transformer model, and then we have the optimizer, then we have the criterion, which is the cross entropy loss. We call the model train. We send the model to device. We send the criterion to the device. We wrap the model and optimizer with the Intel extension library. And here comes our training loop. We send our source and targets to the device. We call the optimizer. We put our output somewhere, calculate the loss based on the output, run the backward pass, and take an optimizer step with updates from what we have learned in the backward pass. Okay, I will not go over the multiple GPUs now. We'll see what's the situation here. Okay, it has started running. It's printing things from rank 10, 11. So it has not crashed yet. What's up with you guys? Have anyone tried to run the first script? Yes. No, you cannot do it. You cannot do it because this code is written to explicitly look for GPU. Login node does not have any GPU. See, order. See if you can. Okay, it looks like we have had some success among the folks. And now I will try to run the script that should generate some profile for me. And let's see if that comes out okay. Profile. So for this one, if I go to the you see that it's basically the same thing that we had seen before, except I have two more lines, lines 15 and 16. We have a variable, capital N, which is 2, and the ppn is 2. So for the profiling, what we are trying to do is generate traces only for 2 ranks. Why? Because we have just seen we can run in 12 ranks, but when we are trying to generate profile, why are we doing on 2 ranks? So generating the profile can be a resource-intensive business because there are processes and hooks under the hood that needs to run simultaneously along with our application and gather samples and data that appears as the timeline traces that we see. So to be able to successfully finish my workload and gather data from all stages of the workload, we try to minimize the number of ranks being traced. So I have tested this code, and we can actually run and trace all the 12 ranks, but usually rank 0 on each of your nodes, tracing them gives us a fairly reasonable idea about what's happening. And then if we need to focus on some area or do double down, have I run out of time? We focus and try to run more and more ranks, okay? So we will quickly run this, and that will be our So I think I have run out of time, but I am around and we will run through this exercise today and talk to you a lot. I really wanted my users to get going instead of me talking about pre-made pictures, but I have put example traces inside the directory in the repo. So if we do not end up generating the traces ourselves, you can load them in the Perfecto viewer and take a look at them and see. So I have also put some pointers in the markdown file, what to look for, what are the things that we like. And so if your run has gone successfully, you should see a traces directory come here. You go inside the traces directory, and you will see PyTorch 2.8, PyTorch 2.8, and inside that, you have a time-stamped directory which should have 2 text files because we have generated trace from 2 ranks and 2 JSON files. These JSON files should go in the browser, and the text files should give us the list of kernels that we have ran, how long it took, etc., etc. Okay. Thank you very much for your attention. I will be around. Please come to me, and we will keep doing this. Thank you.